Hello, in this video we're going to discuss torsion of members with non-circular cross sections, and we'll look at a few notes on power transmission. First, we'll just do a quick review of circular cross sections. You may recall that our maximum shear stress is equal to our torque times the radius divided by the polar moment of inertia. And here we see that the maximum shear stress occurs at the outside circumference, and that's constant all the way across, or all the way around the circumference. The angle of twist over the entire member, that's what we see with these marks, that's equal to the torque times the length divided by the shear modulus and the polar moment of inertia. The polar moment of inertia for a circular section is pi over 32 multiplied by the outside diameter to the fourth power minus the inside diameter to the fourth power. And for a solid circular section, we see that the inside diameter is just equal to 0. So J is equal to pi over 32 times d to the fourth power. Now let's look at torsion for non-circular cross sections. When calculating the angle of twist for non-circular cross section, we're going to use K instead of J, and that's going to be a function of our geometry. We'll refer to a table in the next slide or two to see where K comes from. To determine the maximum shear stress, we're going to use this equation here where we see that tau max is equal to our torque divided by Q, and once again Q will be a function of geometry. And here we have table 4-3 where we see different shapes and cross sections, and this goes on for another slide as well. But let's look at this first slide. Here we can see that we've got K and Q, and you may recall from our previous slide that theta is equal to TL over Kg, and that tau max is equal to T over Q. And so we can look for the various cross sections to determine what K and Q are equal to. One thing to note is that these black dots, they represent the maximum shear stress, or the location for the maximum shear stress for the different sections. For the circular cross section, we recall that it was even and constant about the circumference, but for these non-circular sections, they have high stress points. You may see when looking at these sections that the height and the width for the rectangular sections are not the same, where for the solid rectangle we have a width of 2a, and a hollow rectangle we have a width of a. And this is similar for the heights as well. And so we just got to be careful that we're using the right values for our a's and b's, that what we see here for 1K is not the same for another section. The last thing that we want to pay attention to is this note concerning the inside corners of our hollow square and our hollow rectangle on the previous slide. And it states that the corners, the inside corners, may have a higher stress if the radius is very small. And we'll get to stress concentrations fairly soon, but the assumption that we're making is that we have no sharp corners, because if we were to have a sharp corner, we'd have what's called a stress concentration, and those inside corners may indeed be the high stress location. So if we make the assumption that those inside corners, those inside fillets are large, then the high stress locations remain on the outside surface as noted by the black dots. Let's do an example where we compare the angle of twist of a 2" by 2" by 1/8 inch hollow square tube to that of a 2" by 2" solid square bar. So to compare the angle of twist of the hollow section, the angle of twist of the hollow is equal to the torque on the hollow times the length of the hollow section divided by the K, which is that geometric property of the hollow section, and the shear modulus of the hollow section. We're going to compare that to that of the solid section. So the torque of the solid times the length of the solid divided by the K of the solid and the shear modulus of the solid. But we're going to need to make some assumptions. The first assumption is that we're going to have similar materials so that the shear modulus of both sections are going to equal and cancel one another. the length of both sections, the hollow section and the solid section, those are both going to be equal, as well as the torque applied to both sections. So we see that when we're comparing the angle of twist of the hollow to the solid, we're really comparing the 1 over k of the hollow to the 1 over k of the solid, or k of the solid to the k of the hollow. So let's look at the k of our solid section. We see that the k of the solid section is equal to 2.25 times a to the 4th power, and this entire height is equal to 2a. So 2a is equal to 2 inches, so therefore a is equal to 1 inch. So k is equal to 2.25 times 1 inch to the 4th power is equal to 2.25 inches to the 4th power. The rectangular section is slightly more involved, where we see a and t is equal to, a is equal to 2 inches, and t is equal to 1/8 of an inch, or 0.125 inches. And so here we have k is equal to 2 times 0.125 inches squared times 2 inches minus 0.125 inches. That's raised to the 4th power. And we have 2 times 2 inches times 0.125 inches minus 2 times 0.125 inches squared, and that equals 0.824 inches to the 4th power. And so now we compare the two, theta h to theta s. That was equal to ks divided by kh, and ks is 2.25 inches to the 4th power. kh is 0.824 inches to the 4th power. And we can see that our units cancel, and we have a value of 2.73. And what we're saying is that our hollow tube, given the same torque, shear modulus, and length, the hollow will twist 2.73 times more than the solid. Now let's discuss power transmission in shafts. Power is simply the product of the torque times the rotational speed omega. The units we use in the US customary system is either foot-pound times radians per second, or we have 1 horsepower, where 1 horsepower equals 550 foot-pounds per second. In the SI system, we have Newton meter times radians per second, which is equal to 1 watt, or sometimes we'll see as 1 joule per second. Rotational speed. Usually we describe rotational speed as revolutions per minute, RPM, or sometimes we state it as a frequency, where we have 1 cycle per second is 1 hertz. When calculating power, we must use omega with radians per second. This is required. So converting is necessary, where we have omega is 2 times pi times n divided by 60, and n is the number of RPM, or we have omega is 2 pi times the frequency. Once again, whenever we are calculating power with our power is equal to torque times omega, we must have omega in radians per second.